And let's take a look at one last example of curve sketching. So again, you're not really making another tab, you're just tearing another piece of paper underneath it. And this one's going to be, I'm going to put a title, Finding a Cusp, because what happens if there's a cusp in the curve? We haven't talked about that. So one last example. Right, so the question is, what happens if the derivative is undefined? In other words, when you set it equal to 0, well, their derivative doesn't exist, so you can't set it equal to 0. What happens then? So in that situation, you might have a cusp. Okay, and just in case you forgot what it looks like, that's what it looks like, to check for. So it looks like a V. It's like when the slope changes abruptly. Alright, so really, again, remember, derivative means what? The slope. The slope of what? The tangent line. That's a listening check. So you're going to complete my sentence here, slope of tangent line. That's your listening check. Alright, as x tends to c from one side, it doesn't matter if it's from the left or right, it's positive infinity, and then as it tends to c from the other side, it's negative infinity. That's what it means to have a cusp. So if the slope of the tangent line from one side is infinity, but the other side is negative infinity, and it's still continuous, then you have a cusp. Alright, so looking at this example, so let's start with everything of this function. Let's start with the function, everything from the function. So number 1, x-intercept. X-intercept, y is equal to 0, or f of x is equal to 0. So put that function equal to 0 and solve. So I'm going to take the negative x to the 2/3 on the other side, so it's going to be positive. Then I'm going to rewrite it in cube root and squared. Then I'm going to cube both sides so I can get rid of the cube root. Then I'm going to take the square root of both sides, and I'm going to simplify it. So 2 radical 2. That's the x-intercept. The y-intercept is where x is equal to 0. So put every you see an x, put it equal to 0. So this is going to be 2 minus 0 raised to anything is 0. So 2 is your y-intercept. Again, put a box around it, color it, just so that you can find the information when it comes time to get it. Let's start with the slant isotope. There is no rational function, so there's no slant isotope. This is a listening check. Underline the word not a rational function, or the words not a rational function. Again, box it so you can find it. Alright, let's take a look at a vertical isotope. Just to remind myself, I'm going to draw it again. Here's a vertical isotope. It's a limit as x tends to a number. So it's limit as x tends to c of the function is equal to positive or negative infinity. For that to happen, it's a rational function where the bottom is equal to 0, remember? That doesn't exist here, so there's no vertical isotope. Alright, let's take a look at a horizontal isotope. It says the limit as x approaches positive or negative infinity, it goes to a number. That's not true, because if I plug in positive or negative infinity, it's not going to a number, it's just getting more positive or more negative infinity. So that doesn't exist at all. So there's no isotopes at all in this problem. And the final thing to do with the regular function is to look for the symmetry. Notice how I keep saying them over and over, because you have to know all of these. Alright, symmetry says you put negative x, if you get the original function back out, it's even. You get negative of the original function, it's odd. An even function means it's symmetric about the y-axis. An odd function means it's symmetric around the origin. Memorize it. Alright, put negative x where you see x. So it's going to be 2 minus negative x raised to, and I'm going to write cube root so I can see it. That's going to be x squared cube root, which, look, original function. So at this stage, it's even about the y-axis. This is a listening check. Go ahead and color f of negative x only. Color f of negative x only. Alright, let's take a look at everything derivative. So first, let's take the derivative. So it's going to bring the power down. That's going to be negative 2/3 x to the negative 1/3. Just subtract 1. Equals, I'm just going to rewrite it. Put that on the bottom, make it positive. I want to put the cube root, it's easy for me to see it that way. So critical points happen when it's equal to 0. So put it equal to 0. Remember, for a rational function, if the rational function is equal to 0, the top is equal to 0. Negative 2 is not equal to 0, therefore there's no solution for critical points. So here's the problem. It's not defined at x equals 0, because when x equals 0, you're going to have negative 2 over 0, which is undefined. So the derivative is not defined. If that happens, then you might have a cusp, but it's only there if it's continuous. And as x approaches 0 in this case, from the left and from the right, they go to negative and positive infinity. So let's check it out. So the limit as x approaches 0 from the left of the function. So from the left, it gets really, really small by the negative. It's going to be negative at the bottom, negative at the negative is positive. So this is actually going to go towards positive infinity. Again, you need to relook at limits if you're not sure what I'm doing. Limit as it approaches 0 from the right, so the bottom is going to 0. It's going to become very, very small. But from the right, which means it's positive, and negative divided by positive is negative, and it's going to be infinity because anything divided by something so small becomes really, really big. So that there's a cusp at 0, 2, because the limit from the left and the limit from the right are opposite of infinity. Opposite signs of infinity. I don't know how else to say that. Alright, so now we're going to take before we take the second derivative, I'm going to prepare my table, my interval for what happens at interesting points like isotopes, cusp, and such things. So I'm going to make my table, interval, test numbers, sign of the derivative, and what conclusion I'm going to draw from it. As a listening check, go ahead and color in the box, when you draw the box, of the word conclusion only. Color in conclusion only. Alright, now I'm going to take everything second derivative. So taking the second derivative, what am I looking for? I'm looking for inflection points when it's equal to 0. I'm looking for maximums and minimums from the critical points. So second derivative is inflection points. If there's no first derivative, critical points, there's not going to be nothing on second derivative, but I'll go ahead and do it anyway. So here's my first derivative. Take the second derivative, so negative 1/3 times negative 2/3. It's going to be positive 2 over 9. X to the subtract 1 more is going to be negative 4 over 3. And putting it in terms of square roots. Alright, so again, that's going to be equal to 0. If it's a rational function, it's the top must be equal to 0. And 2 is not equal to 0, so again, no solution, no points of inflections. Because there wasn't one for critical. For the first derivative, it's not going to be one for the second derivative. You can look at end behavior too, but I have enough information to graph it. Now let me take a look at what happens at these interesting points. So isotopes, with no isotopes, I need to know what happens at the cusp at 0, and then no inflection points, no critical points. So basically less than 0, greater than 0. I just need to know what happens before my cusp. So test numbers, then plug it in. So if you plug in negative 1, I'm going to look at the square root 1. If you plug in negative 1 at the square, let me just write it down. So f prime of x equals negative 2 over 3 cube root of x, because I can't deal with exponents that are not that. So plug in negative 1. You're going to get a negative divided by negative, which is positive. The top number is always negative, and then if you plug in positive numbers, you're going to get a positive on the bottom. So negative divided by positive is a negative. So it's decreasing. So let's plot this. I actually don't need so much space on this. Let's go, each line is 1, and you just need to go like 3 high, 3 low, 4 to the left, 4 to the right. That should be good. And then just plot what you know. So x and y intercepts is 2 plus or minus 2 radical 3, which is about like 2 point something. Let's put it there. Positive, negative. We have a cusp at 0, 2. And then from the left it's increasing. So it needs to be increasing, going through my x-intercept and stopping at my cusp. And then it's going to dramatically decrease because it's symmetric. It's going to look exactly the same, so symmetric, but on the other side, and it's decreasing. That makes sense because that's decreasing. And bam, there we go. There's the graph for 2 minus x to the 2/3. Alright, so you really need to practice, and step by step without looking at your notes. Let's practice.